welcome back to another video for Math 110 Intro to Number Theory. And in this video we're going to talk about the Lehmer sieve, which is an early electromechanical device that was, you could call it a digital computer, and it solved certain sorts of simple diophantine equations automatically. And in particular some second order ones that since we've been talking about quadratic residues and such, it seems like it's an appropriate time to talk about this thing. So here's a problem that it can help with, which is what are the divisors of a large natural number n? So the naive approach that we've talked about before is trial division, where you just check to see if n is a multiple of 2, n is a multiple of 3, n is a multiple of 4, and so on. And you can stop at the square root of n rounded down, because any divisor is larger than that. N divided by that divisor will be among these potential divisors. So let's say that we have a large number, like 2 to the 1024. Well, this would be very slow, and it would take about 10 to the 156 years on a very fast computer. I was assuming that it would be like assuming that it runs at like 3 gigahertz and it's able to do a full division of these gigantic numbers every 10 clock cycles, which is kind of unbelievably fast. So one question is, are there any tricks? We're not going to answer, there aren't any real good tricks because, things depend on factorization not being easy, like RSA. But still, can we at least divide the cost of doing this by some amount? We won't be able to factor such large numbers, but we'll learn some stuff. So the Lehmer sieve, so this was designed by some Berkeley math professor and his son, who ended up also being a Berkeley math professor. And the way it worked is that there are all these chains, and the chains had pins on the edges of them, and at the very top are these fingers that would detect when it is touching one of these pins. And there's also a drive shaft that's driving all of the chains simultaneously. And also, if each of the pins is in contact with one of the fingers for each of the chains, then it would cause the drive mechanism to stop. And then also there's a readout to say how many chain links have moved across the bar. So anyway, if you can encode your problem into a bunch of pins on chains of different lengths, then you can just have it run automatically, perhaps over a couple minutes, overnight, or over a week, and get some number out that is some solution to some equation, at least modulo the least common multiple of all the lengths of all the chains. So this is a version of it that is in the Computer History Museum over by Stanford. So how can this be used for factorization? So one thing, let's just assume our number is odd, because if it's even, we can divide it by 2 pretty easily, even by hand. And we can repeatedly divide by 2 until it's odd. So an important lemma here is that if n is odd, then the number being composite is equivalent to their existing x and y solving this diophantine equation. N equals x squared minus y squared. But we do also want this condition that x is greater than or equal to y plus 2. One thing is we do need x to be bigger than y, otherwise this will be negative, or 0. And we'll see why we want the plus 2 instead of just saying x is greater than y. Okay, so let's prove the this way first. So we assume that we've got a solution of that type. Then the important thing to note is that x squared minus y squared factors as x plus y times x minus y. And since we've assumed that x minus y is greater than or equal to 2, then we have we have a factorization with 2 factors greater than or equal to 2. So it's composite. So let's go the other way, assuming it's composite and odd. So let's let a and b be factors in a factorization, because we assumed it's composite, they exist. And a and b are greater than or equal to 2. So since n is odd, a and b both must be odd because they divide n. And also, by symmetry, one of them is going to be at least as large as the other. So let's just assume, without loss of generality, that a is the one that is at least as large. Then because they're both odd, we can take their average, and that will be an integer, a natural number, actually. And also, a minus b over 2, that's going to be a natural number. And furthermore, if we take the difference of x and y, then what we get is b just on the nose, and that is greater than or equal to 2. So that satisfies that. So rearranging this, what we can do is take n and add squares one at a time to it and see if we get a square in the end. So that's an alternative to trial division. And yeah, this isn't necessarily faster or anything like that, but at least it's going to be amenable to automation in the form of the bicycle chains of the Lehmer sieve. So one observation is, okay, so like, how do you really check if something is a square? Well, one way to do that is to check instead this equation mod m for some modulus. And so the question then is, mod m, is there a y such that n plus y squared is a quadratic residue? So like if there isn't one, then what that means is that n plus y squared is just not a square at all, because every quadratic residue is the square of something, at least mod m. Yeah, so if there isn't one, then it's just not a square. So yeah, if for a given y, n plus y squared is not a square, then because that's being done mod m, that means that, well, n plus y squared is just not a square at all. And also, if it is, then it's just an inconclusive test. So let's just play around, see what this is like. We're going to use n equals 51, the Grothendieck prime, and let's look at what this all is like for m being 5. So mod 5, n is 1. So, well, we take our, the key point here is because it's modulo, that means that this whole thing just keeps looping around. And it's going to literally be looping around as chain around a sprocket. So mod 5, we just have to check 0 through 4. And so we calculate n plus y squared mod 5 for each of these. And here are the squares. mod 5, 0, 1, and 4. And so we see that for these values of y, n plus y squared mod 5 is a square if y is 0, 2, or 3. So if we did have a solution to this, then we would know that y has to be 0, 2, or 3. This is related to something that Gauss called, it was elimination. I just suddenly forgot. The method, the method of elimination. No, method of exclusion, sorry. So the method of exclusion is by like looking at things mod various other things, we can come up with which values are impossible. So in this case, y cannot be 1 or 4 mod 5. Well, and so this is good so far. We only need to check 3/5 of all the numbers. So now let's look at mod 7. So in this case, 51 is 2 mod 7. And we can, for each residue y, we have y squared, and we add n to it. And then we can look at the residues. It's one, or the quadratic residues. It's 0, 1, 2, and 4. And only 2 and 4 down here are the residues. So y has to be 0, 3, or 4 mod 7 for this to even have a solution. Yeah, so 1, 2, 5, and 6 are excluded. To illustrate how much this really does exclude, so because 5 and 7 are coprime, we can apply the Chinese remainder theorem. And so inside the square are all the numbers mod 35, and they are positioned so that the row they are in is their residue mod 5, and the column they are in is their residue mod 7. And since we know y has to be 0, 3, or 4 mod 7, and 0, 2, or 3 mod 5, then that means that only these 9 numbers mod 35 are possible. 9 of the 35 are, so that, yeah, we've excluded everything but 9 of the residues. I'm not going to go through the effort of testing them all, but it does turn out that 7 is a number that when we square and add it to 51, we get an actual square. And so what that gives us is that 10 plus 7 and 10 minus 7 are factors of the Grothendieck prime. For a different sort of problem that this thing could do, oh yeah, I haven't really said how the sprockets will work in the chains, but and then after the next example, I'll get back to that. So a related sort of thing that can help sometimes is, well, okay, so let's look at this potential Mersenne prime, 2047. So we're wanting x and y where it's n is x squared minus y squared. And maybe you think that the factors are going to be close to each other for some reason. So what we did before was we started with y at 1 or 0 or 1, like we could move upwards like that, but we could also try starting from the middle, so to speak, by observing that x has to be at least as large as the square root of n. So we can introduce a new variable k and have x be, I took the square root of n rounded up, so 46 plus k, and then I took this diophantine equation, substituted that in, and then subtracted n from both sides to get this new diophantine equation. So y squared is 69 plus k times k plus 92. And so now the question is, for different values of k, is this expression a square? And so we can consider this modulo different primes. So modulo 3, we can reduce this expression to just k times k plus 2. And I have calculated it for 0, 1, and 2. And 2 is not a quadratic residue, so it's excluded, and the only remaining possibilities are 0 and 1 mod 3. And mod 5, I reduced it again, calculated the values for various k's mod 5. And 2 and 3 are not quadratic residues, so k equals 1, or k congruent to 1, 2, or 4 mod 5 are excluded, leaving just 0 and 3. And also mod 7, I did that too. And so 0, 2, 4, and 6 are excluded because those values do not give quadratic residues. So if we were to then turn this into a bunch of chains that could run on a machine, then, well, we know that k has to be 0 or 1 mod 3, 0 or 3 mod 5, and 1, 3, or 5 mod 7. So if I put these chains onto onto some sprockets, so that's a sprocket, 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 and I put my 3 chain here, and my 5 chain there, and my 7 chain there, and then I turn the machine on, and of course these things have pegs on them, and once all the pegs line up and I have the machine stop, then I can read off a value of k mod 3 times 5 times 7. Because these are all relatively prime chain lengths. And then I can, if that worked, then great. But if it didn't, then I can continue the machine running, and then it will stop and give me the next possible value. So here are the chains with pegs. Okay, so what I did here is I took the chain of length 3, and so there are the pegs in 0 and 1, and I just repeated it over and over and over down the line. Because what this is gonna what this represents, I guess, is it's kind of like a slit scan camera. As the chains are going past our view, we're just recording through time which pegs we're seeing on which chains. So according to this, okay, so as it goes along, there's peg, peg, no peg, peg, no peg, peg, no pegs, but then 3 all line up, so then the machine stops at k equals 3. And then we can plug it in and see it didn't work. And then it keeps, when we run it again, then it will stop at k equals 10. And it actually does end up working in that case. But anyway, if it didn't, then we could keep it running. And let's see, it lines up again there. So they're only, out of, the 33 or 34 numbers that we would have had to try, there are only 4 of them that actually do, because of the help of this machine and running basically the Chinese remainder theorem along with a bunch of congruences, linear congruences that we've reduced the problem to. So if we want the machine to stop even more infrequently, we can add another chain. So I've computed where all the pegs would go on that chain. And so this one, it would stop first at 10, and if we ran it again, the next time they all line up is at 33. So, half as many still. And it doesn't slow the machine down at all. It's just like as many chains as you can put on the machine, and also as many chains as you can actually conceivably design, because it does get more and more labor intensive as there are more pegs to calculate. So anyway, so we ran our virtual machine. The chains span around. I guess this one, the 3 chain one goes around 1 whole time, 2 whole time, 3 whole time, and then a little bit. The 5 chain 1, 2 full revolutions. The 7 goes a little bit through its second, and then the 11 wasn't even done, so we didn't really need the machine. But anyway, we can check that 69 plus 10 times 10 plus 92 is 33 squared. So that's y, and that was k. And this is x, which is 46 plus k. So what we got was 2 to the 11 minus 1 is 56 squared minus 33 squared. So the average of those two numbers, 56 and 33, is one divisor, and the difference over 2 is another divisor. Oh, no, I didn't mean it. I meant the sum of the two numbers is a divisor, not the average. And the difference was another. So 23 is a divisor, and, well, whatever the other number is. So, so that's an example of, I guess, using machines to use here, let's look at the sieve one more time. Yeah, so we had our little chains running through, and we stretched out looking at what it would look like in time, and we showed that a particular potential Mersenne prime was not actually a prime. Okay, well anyway, that was a short video about that. I'll see you next time.